Good morning, everyone. I hope you had coffee, a bit of breakfast, you are awake to start with the first session for today. The session today has the name of Next Generation Battery Packs for Battery EVs and Plug-in EVs. So, as you know, the European environmental policy for climate neutrality by 2050 is pushing towards rapid implementation of transport electrification. So I will be the moderator for this session today. My name is Martha Yalabuki. I'm a project advisor at CINEA, the European Climate, Infrastructure and Environment Executive Agency. And I'm here today with my co-moderator, Bozorg Kanbay. Thank you very much for stepping in, because we had another co-moderator, but because of today's national strike, couldn't come. So thank you very much, Bozorg, for being available and help us. I will start with some more details about this session. So, the 4 projects that will be presented today, they are funded from 2020 call on next generation and realization of battery packs for BEVs and PHEVs. So one of the most important parts there is that they need to have performance improvement of EVs by reduction of 20% battery system weight for mid-size battery electric cars. Another objective is that this project needs to have a 25% shorter discharging time with a 150 kilowatt charger compared to best-in-class electric car in 2018. They need also to achieve battery life to 300,000 kilometers in real driving, referring to a mid-size passenger car, using improved battery management, balancing and thermal management during high-power charging discharging. They need also to contribute to circular economy goals by 20% life cycle analysis improvement compared to existing products. Also, they need to improve module and pack sensorization and thermal management. So, we'll start with the first project today. It's Liberty. The presentation will be given by Werner Leitbeck. He is lead researcher for battery crash safety at Virtual Vehicle. So Liberty, one of the main points is to develop a battery system that provides electric vehicles with a range of up to 500 kilometers and ultra-fast charging capabilities, achieving a lifespan comparable to combustion engine vehicles. Also, the project focuses on creating a lightweight battery system that enhances vehicle efficiency while ensuring improved safety standards by incorporating advanced materials and innovative structural designs. Finally, the project includes increasing battery durability to extend its usable life, optimizing second life application for energy storage, and ensuring efficient recycling at the end of life. So, Werner, the floor is yours. And also, you have 15 minutes. I will stand by after that. Thank you very much.
Thank you very much, Marta. Good morning, everyone. It's very early. It's a pleasure to being able to present about our Liberty project. I'm not the coordinator of this project. We as Virtual Vehicle, we co-coordinated with the colleagues from Ikalan. And let's immediately start into what we did and what we were. We are a project of 16 partners. We all started or actually finished our proposal writing process during the first signs of Corona back then. And we're very glad to be selected for funding and had our first 1.5 years in most of the time, lockdowns, not lockdowns. So very challenging time to surround this multitude of partners, multitude of companies. Great consortium actually from 7 countries. We have Mondragon University and Icalar from Spain. We have NXP, Valeo and Hutchinson from France here. Flanders Make, Bring, and Flanders Make, Bring, and Klepa from Belgium, of course, and NXP from the Netherlands, and from Germany, Diehl, Acorec, Infineon, Mercedes, and Fraunhofer. And last but not least, Infineon from Romania also supporting us. Very last but not least, we are Virtual Vehicle from Graz in Austria. Originally, this project was to be done in 42 months. Very challenging times, very challenging topics actually to deal with. So we were granted a 6-month extension and were able to successfully, in our view, finish last December. So this is a very recently finished project, and I'm very happy to be able to present today results on this project. Our objectives, as Marta already summarized more or less, to achieve a range of around 500 kilometers with a fully charged battery pack, to achieve a very short charging time, ultimately safe battery system. Back in the day, this was even much more a critical issue. Everyone was afraid of vehicles burning all the time. To achieve a very long battery lifetime, also a very critical issue here. And as we heard already yesterday in our last panel session and a couple of times before, sustainability, circularity, life cycle analysis is a very high and important topic in designing a battery, designing vehicles and highly integrated ones specifically. Okay, I will talk today about some of our results, some of our needs, and this will be specifically the cell-to-pack design. I will talk about our innovative immersion cooling system. I will touch the safety and thermal runaway issues we faced and solutions we provided for those. Talk about the BMS system and some cloud algorithms there, about the LCA analysis and LCA by design topics there, and finalize then my speech with our performance testing results here. Okay, cell-to-pack design, something many of you have heard. What is it all about? We need to put as many cells, as much battery energy into our available space in a vehicle, in every kind of topic where space and weight is a limiting factor. Higher energy density, higher power possible. So we have a very lightweight housing, decreased mass by around 20% here. In this case, we replaced the aluminum housing parts with organo sheets from Valeo. They are recyclable and especially lower the weight here. And highly integrating a cell-to-pack approach means a highly integrated cooling system, and we'll talk about it a little bit later more. And we also integrate here an active and a passive safety system directly in the pack. And last but not least on this topic, lightweighting cannot or should not stop on integrating the cells. It's about all the components around, and we selected 2 of them that were replaced by very modern, very small, very lightweight alternatives to the current ones. This is a low power pressure sensor and a semiconductor-based main switch was developed. You see that on the upper right here, our low power pressure sensor, and the red thing here, the lower one, is the complete replaced main switch with the upper components that are a lot heavier and a lot more bulky on the lower part of the photo here. Okay, immersion cooling system, that was mostly developed by Valeo and integrated in our available vehicle and battery pack system. Thermal management always is a trade-off between affordability, safety, performance, and durability here. And high charging time, low charging times, increasing charging always involves a generation of heat, so a very efficient battery cooling system here is of high relevance. For our battery pack, we resolve to a partially immersed cooling system here. So part of the cells are immersed in cooling with a dielectric fluid with a very enhanced heat transfer. We have around a flow rate of 3 to 4 liters per minute for the whole pack. So this is rather on the low side, but enables very efficient cooling. And we cool our bus bars directly because we have this cooling system has some kind of spray cooling with nozzles on top here. You see the orange part where the cooling fluid is distributed and sprayed over the cells. Sounds a little bit fancy, is a little bit fancy, but works very, very well and gives us additional features that I will talk about in the next slide as well. Also integrated in the cooling circuit is the battery main switch that, as it is semiconductor based, also needs some cooling. Yeah, okay. Then, one of our premises, focus topics was enhanced battery safety, battery pack safety. We all know safety comes from many different areas in the battery. You need stable cells. You need a clear BMS system in order to do not overcharge and charge them. You need a clear strategy there. But one of the critical issues that everyone has in mind is the so-called thermal runaway. That is when the cell chemistry, for whatever reasons, goes into internal self-combustion and reaction and produces loads of heat and fires, burning and toxic fumes. We need to absolutely prohibit propagation of thermal runaway on cells, and that's what we try to do here. We have an active safety system here involved with boiling compartments that can be put around modules, so to contain a thermal runaway in a module. Then we have a passive safety system from Hutchison as well, with lightweight sheets that you can put between single cells, between cell stacks, or between modules as well, in order to really block or delay thermal runaway propagation, assuming that a thermal runaway event on one cell cannot be completely avoided at 100%. And yeah, for this we did a lot of testing at virtual vehicle actually, thermal runaway testing on the test bench, on cell level, on complete cooling system integrated to a stack of up to 12 cells here. And we were able to show that thermal runaway events can be blocked, can be prevented, and that together with our spray cooling system really prevents thermal runaway propagation, blocking and reduces fire. In addition to that, crash safety is one of the potential triggers for a thermal runaway event. So we did quite a lot of cell testing, understanding the mechanical characteristics of cells. We are using metal can cells here of high energy density with NMC chemistry. And what we could show in this project is that dynamic and static performance are quite different, and the cells, especially in this loading direction, can be loaded with up to 115, 20 tons of force here. So these cells are very durable until short circuit occurs, and we showed that here integrated in a cell and using a short circuit device here as well to find short circuits in simulation. So this is something to explore even more and allows integration of cells into the battery pack much better. Our next topic, BMS and algorithms. We used the Fraunhofer Fox BMS specifically adapted for Liberty here. Fraunhofer was part of the consortium and served all the application of the NXP slave. The cell contactor system has been laser welded and very efficient and as I mentioned before, is also fully immersed in the cooling fluid. Apart from that, we prototyped here a cloud-enabled platform to remotely troubleshoot, organize, and deal with our battery management system things we have to do. And yeah, can do SOX modeling there, battery management system, recalibration, troubleshooting, and these kind of things. So it's fully data-driven and learns online here. Fine. Last of our big design challenges that we had to integrate from the very beginning in our pack design was LCA, with relatively high and critical goals to be reached. What we found out that whatever we do, the cell manufacturer itself will always have a very high impact on our LCA analysis here. Higher energy cells, more cell chemistry in there. This is a given. But due to all our efforts, longer lifetime, higher charging, we can give a much longer operational phase to our battery system, much longer life, and that contain the critical factors there. So overall, we have a much higher efficiency on our battery pack compared to the ones that we compared to. And we also could reduce the use of raw materials quite a lot, by up to 70%, by efficiently being able to recycle batteries in the end. We heard yesterday that currently a lot of black mass, so that's the battery contents in the end, go to Korea, go outside of Europe, but colleagues from Acurec were definitely able to show that with a high recycling rate in Europe, we could save on rare earths and the critical components of batteries here. Overall, we were able to show some 30% better life cycle assessment here. Then, as our project has finished, we are very happy to being able to test our battery system, our full battery system you're seeing here, on test benches and do the complete part here. We did battery assembly, functional testing, a lot of performance and safety testing on cell and stack level. So this was then all extrapolated to complete life cycle here. And then we also had our full battery system you see here, integrated in a Mercedes EcoC vehicle. Was fully working, the system, and yeah, we were very happy about that. You know, this is always a very critical time. It's very late in the project time, so you should not fail in too many areas there when doing all those tests. So we were able to validate our performance requirements, testing all the customer relevant specifications like fast charging range that we put on ourselves under road conditions here. And we did a lot of safety and ABUS estimation in a simulation-based, full vehicle-based environment there. Yeah, and as I said already, the battery was integrated in the Mercedes EcoC, and that could comply with our requirements and specification. In the long run impact of our project, we had our project final result at Mercedes premises in December. We could actually see the battery back there. We had it there. Lots of discussion. Could basically touch it, but not for safety reasons, because this was the full life battery back there. Was nice meeting lots of people there and discussing. In general, what we are doing, or what we were able to do, showing that 500 kilometers range is achievable with a battery on cell technology that is, of course, we all know that, based on cells that we were able to purchase 4 years ago. So with the same technology, we could go even further currently. That reduces the anxiety on the electric vehicle markets and should enable a higher penetration on electric vehicles in the market itself. The same thing is with charging time. With our high-end cooling system, we were able to really reduce charging time a lot. Coming to numbers later, charging time is one of these range anxiety problems as well. This helps it a lot. We have a very safe battery system here, can show that batteries can be integrated in a very safe way. Also, if there is a thermal runaway event on one cell, we were able to contain it within the battery and stop it. So we do not have a battery burning for hours and hours without being able to stop it. Our system is really able to stop the battery, stop the propagation, and allowing everyone to safely exit the vehicle, and yeah, having an impact on public in this case here. We have a longer battery lifetime that increases the sustainability of the vehicle, of course, and the value chain, and yeah, also enable the second life for our battery, and thus adding to all the required parts in this context. A little bit more in numbers here. I would just like to tell you what we did there. We were able to increase the battery system capacity by some amount here. We were able to reduce the battery weight. We also take into account here that the cell chemistry there takes its part, but the battery system weight itself could be reduced quite drastically here. The vehicle cross weight could be lowered, containing the same battery capacity. The range could be increased. We achieved a full mileage of 300,000 kilometers. That's a huge increase over the mileage that was originally in the vehicle there. We have a very high allowable charging power for fast charging times if needed, so we really could use that a lot with our system. We have an active and passive safety measures in there, allowing thermal runaway propagation prevention, so it's really able to prevent that stuff. And yeah, our battery life could be increased by 100%, and on the LCA part, we were able to reduce 21% on CO2 emissions, or up to 70% and antimony equivalent raw material shortages issues that are currently all the time in discussion. So I think we were able to show quite a lot here. Thanks a lot for listening to me. And if you have any questions, I will be here for the rest of this session, of course, but also for the rest of the day for some reason, till the very end. And my colleague Eduardo from Michelin is also available via email and most likely listening to my presentation here now. Thanks a lot, and I hope it was not too long.
Thank you very much, Werner. I understand it's very difficult to have like 4 years of project in 15 minutes and discuss them. Very interesting presentation. Just a reminder for the audience, please, keep your questions for the end. We have a dedicated Q&A session, so there you can ask our presenters or comment. Also, when you would like to intervene in the Q&A session, I would like just to remind you to state your name and affiliation. So, going to the next project is MARBEL. So, the presentation will be given by the coordinator of MARBEL, Edouard Piqueras-Hover. He is an R&I project coordinator at Eurecat. So, MARBEL is developing a compact, modular, lightweight, and high-performance battery pack with increased energy density and reduced charging time, enhancing vehicle efficiency and user convenience. Also, the project is implementing eco-design principles to ensure the use of recycled materials, facilitating easier assembly, disassembly, and recycling process, thereby minimizing environmental impact. The project also developing a flexible and robust BMS to optimize battery performance, safety, and lifespan, ensuring reliable operational in both battery electric vehicles and plug-in hybrids. So, Edward, the floor is yours.
Okay. Thank you, Marta, for the introduction. And, well, thank you, all of you, for coming today, and to the Batteries Europe Partnership for the invitation and opportunity to present. As As Marta commented, I am project coordinator in Eurecat Technology Center, a research technology organization in the region of Catalonia in northeast Spain. And well, I'm glad to present you a bit the work we've been done during these years. MARBEL is a project from the call that Marta introduced at the beginning of the session. Okay, that we planned the project for 3 years and a half, but we needed to extend it. And actually nowadays, we are finishing the project. By the end of March, we will be finishing. So our battery is actually now in the test bench running cycles, etc. So you will see I don't have the final numbers of performance in use phase like our colleagues in Liberty. But I wanted to advance you that in the 19th March, Wednesday, we will be in Torino in Stellantis Research Center Fiat presenting the results of the project, and I invite you all to traveling to Torino, or also it's a possibility to follow it by online, okay, from your computer. You can see it, you can check it later in our webpage, and that's the publicity for the advertisement for this presentation, okay. Let's go. Let's move. This project, we formed the team between different research centers. You see there Eurecat and IREC in the region of Catalonia, in Spain, then partners from Germany, the Technische Hochschule in Ingolstadt, SINTEF, Fraunhofer, ICCS in Athens. We also worked with tier 1s, manufacturer of components for the housing, extruded aluminum housing asses. We also worked with fasteners manufacturer, Agrate in Italy, ABL as a battery manufacturer, Ficosa for the high voltage power systems in the battery. We are assessing also the end of life of the battery, so we count with a company dedicated to the disposal and dismantling of batteries. An automotive engineering that is working on testing the battery. And finally, 2 other SMEs working particular elements for the communications of the battery and the BMS. Our reference OM is Stellantis through the participation of their research center in Fiat in Torino. Okay, well, our objectives, what were the objectives of MARBEL in the frame of this call? From one side, we wanted to accelerate the market uptake of the electric vehicle, okay, and get, at the end, more efficient but also more sustainable electric vehicles. Okay, that's with the aim of the contribution to the European Union policies and this target of reduction of greenhouse gas emissions by 55% by 2030. How we could do that? By increasing the energy density of the battery packs, that it's by reducing space and weight. Optimizing the battery system's performance to get an increased battery range and also battery lifespan, reducing the charging time, and also reducing time and cost for manufacturing, but also important for the maintenance of these batteries that goes to the electric vehicles, and facilitate the repurpose for second life and environmental impact, okay? Up to which numbers? No, this increasement of energy density, our target is 0.156 kilowatts hour kilogram. We aim to reduce more than 20% the weight of the system, excluding what's the weight of the cell, that we are not working on that part, and increasing battery lifespan. Up to 300,000, increasing charging time, and setting a very ambitious target or goal in what is the improvement of the environmental impact. Okay. Okay. For us in our project, one of the main important topics is to work on a battery that can extend the life and the value of that element further than the automotive life. Okay, we believe that one of the ways to be competitive is to produce products that can get a value because they can be reused in other several uses. And we have a very high performance element product, but then it can be easily maintained and easily repurpose it for second life. So we reduce impacts, but also I think we increase the value of that product. So for us, the circular design in the high-performance battery pack, it's a very important topic. We developed, that was one result from EURECAT Technology Center, a methodology to enhance the environmental and sustainability of the battery pack through targeted eco-design actions. Okay, how we define these eco-design actions? We focus it on the 4 stages of life of battery. That is where the raw materials come, how we manufacture the components, etc. What happens during the use phase of the battery, how it performs this battery. Also the repurpose on second life, and what happens at the end when this product or these parts of the battery are not more useful, so we need to dispose. So we started identifying where are the hot spots in in these 4 life cycle stages, where if we act implementing eco-design actions, we will get a major gain on reducing impact. Okay. We established the most properly eco-design actions or strategies based on the previous conclusions of step 1. Then we aligned all the partners, tier 1s, manufacturers of the different components to implement a technology strategy to implement those eco-design actions. So we saw, okay, one very clear, it's like let's reduce the weight so we can expand the range. So in the use phase, we get less impact, okay? How we reduce weight, and that would be an example. Or we want to repurpose modules into a second life, how we facilitate this in the design, no? And then we get together, since we take advantage that all the partners of the value chain in the battery were in the consortium, or almost all of them, to work on this. So finally, we selected concrete eco-design actions, and we implemented in the design, okay? And then also we will measure what's the impact of each eco-design action in reducing the different environmental impacts of the battery. Okay, so we ended up with a modular, scalable, and lightweight and thermally optimized design of the battery. Well, with the different modules, 32 modules is a 800 volts battery pack, electrical and electronics, thermal management distribution components. All of them are screwed to the housing, so it is easily to remove for maintenance or for repurpose of those components when the battery ends the life in the automotive sector. All the weldless, the fasteners of this battery are weldless, so they are weldless bus bars and cell-to-cell connection. This was a result from Agrati, a company in Italy. We have a switchable architecture for 100 volt, 800 volt, with a junction box designed by Ficosa that permits this, and they have worked on this part of the reduction of charging time, and enhanced thermal management with high-efficient cooling panels, and the functional aluminum profiles for the housing act at the same time as a cooling element, so the coolant goes through our housing. That was a bit tricky or difficult because we are working on extruded aluminum profiles. You will see in next slides. Sorry about it. We are working on extruded aluminum profiles, and we needed to weld it, and there are all the holes for screwing, the channels where the coolant passes, etc. So it has been a very challenging work of design and welding and joining. The part of the joining, there were a webinar yesterday managed by Sintef. You can see results there. Another action to facilitate transition to second life is the BMS. Okay, we work at a partner IREC and PowerTech and OTC Engineering. They work in an advanced battery management system for eco-design oriented. Okay, and the thing is that this BMS have a part that is connected to the cloud for what concerns all the calculations to facilitate calculations and the algorithms that you will see in the next slide. But it's also designed to be modular and scalable. So it is easy to know exactly with each module what's the status of each module. So facilitate also this information for repurposing to second life. Okay, so facilitating reusability and recyclability. In the cloud, we will be running data-driven digital twin for electric vehicles. That is, it's being developed by Institute ICCS in Athens, in Greece, and on the basis of synergies that advances in other past projects and ongoing projects, Uptime and Mine.io. The data-driven digital twin, this digital twin embeds machine learning algorithms that are providing remote diagnostic of the battery based on early failure detection, predicting upcoming internal battery failures, estimating remaining useful life, and state of health, different state of health variables. Okay, this aims to be an analytics as a service platform. It's one of our key results of the project, and well, I processed here the conceptual architecture of the digital twin, and also the initial experiments they made it on the accuracy of the algorithms they are working for these predictions. And nowadays, well, they are fitting this with real data, data from MARBEL battery to enlarge this result. Concerning the use of recycled materials, and coming back to this eco-design methodology to define eco-design actions, I forget to mention this methodology that was a result in MARBEL is being implemented now in another project that is called Zebra with V, also for this purpose, no? How we implement actions to reduce these impacts in this case in other parts of the car. Here we applied the use of recycled materials that in the case of aluminium have a quite significant opportunity in saving CO2 emissions. In the housing, in the bus bars, and also in the elements that forms the design of the module. For instance, in what is the application in housing profiles, together with ASHAS and SINTEF, as I commented before, we have this extruded, scalable, with extruded aluminium housing. Okay, we analyzed a different percentage of scrap in the alloy, and this is something that we were also working in Salema project, not only with extrusion, but also with high pressure die casting and other processes that are used for housing manufacturing. Well, here the conclusion is that the quality of the scrap is key, and the waste and the process for classification, it's also a key element when getting high performance recycled aluminiums. Okay. Well, mid-term to long-term expected impacts. Well, these are main impacts, no? More sustainable, efficient vehicles, as I commented. Our aim is to reduce impact of the batteries, but at the same time, I think gaining value of the batteries that are built here in Europe by getting this from one side benefit of reducing the impact we produce to the environment, but also gaining a product that have longer life and I think can get more profit from it. We align with the European policies in what refers to the strategies for circularity and reduction of gas emissions. And well, I think we also are providing a pool of skills for battery eco-design, novel BMS functionalities, dismantling, reconditioning strategies, etc. And also the economic part I commented, time and cost. We are trying to design batteries that are easily to facilitate the assembly, reduce the time for assembly, the cost for assembly, and what's very important, to be able to go inside the battery and easily remove components that maybe are not more useful in automotive, but maybe in other sectors, yes, and then replace it and easily get this battery with a longer life, so take more from the same element and not disposing and manufacturing again. Okay, identification of future research needs. I just get some weeks ago about a white paper from sorry, I didn't, well, a World Economic Forum, yes, this publication, I thought, well, this is more or less, let's use this because it's very aligned. So more efficient and cost-effective scrap sorting process, including predictive data analytics. We are using this also for once you know what's coming from your scrap to adapt your process of manufacturing the alloy or injection high pressure die casting or extruding to get this high performance. And there were like an alarm or, well, a notification from European Aluminium that there is a scrap leakage in Europe. And I think any leakage of materials, raw materials in Europe is something that we need to put attention into it, because it's something that we don't have. And standardized and interoperable track and trace platforms. This is very important, and with the new directive of battery, it's increased the policies that push for this to get traceability on environmental, human rights principles when the companies are doing purchasing decisions on what they buy. Well, critical, and also search for information for repair, reuse, repurpose. It's also important to access to standardized data about the state of health, to prioritize, facilitate repurpose and second life. This is something that we work at in MARBEL with this BMS, but also on all this digital twin that provides this and collects this information. And facilitate responsible movement of batteries and battery materials, okay? To build a battery, I think we need brains to start thinking on how to unlock these barriers, to facilitate this movement of components, materials that ends life in automotive, start life in another sector, needs to move from one country to another, etc. And this is something, like circular business models and economy, battery economy, repurpose of second life need to be, well, deserves, I think, to work on it. And I think, yeah, that's the end of my presentation. I think, yes, I make it more or less. And I put this scheme because the focus of MARBEL is in the circularity in that part, no? In battery use, second use. So have the product circulating there, because it's time we move to higher circles. It's more cost, energy expensive. So we need to prioritize the little circle there in use and reuse. Okay, that's all. Thank you very much for your attention. I hope if you have any questions, I will be here the rest of the day, because this, as you know, we are in the Transport Research Congress and there is a transport strike. So we'll stay here, happy to discuss with you.
Thank you very much, Edward. Very interesting presentation. Just a bit of a reminder, I think Edward have already mentioned, from all these projects, Liberty has ended, the other three are ongoing, so the final results are not yet available for the other three. Also, I would like to mention here the Collabat cluster that these 4 projects has created. So they have collaborated together, all these 4 projects. They are very active, they work close together, they have created also, not only for dissemination purposes, this cluster, but also to work together and share lessons learned on different points like testing, BMS, modeling, etc. So it's one of the model clusters that we have in the projects. I'm going now to the next project, which is ALBATROSS. ALBATROSS will be presented by Aysel Pilav, the coordinator of the project, and she's also the research and developer project expert at Yesilova Group. So similar objectives the ALBATROSS cluster has as the other projects, and the developments on the BMW i3 EV ALBATROSS battery pack will be presented, and specifically focused on modules, BMS, tray, dismantling, second life, reuse, recycle, and LCA. So, Aysel, the floor is yours.
So thank you for the introduction, Marta. My name is Aysel, and it's a pleasure for me to present ALBATROSS overview and results to you. Let's start with the overview of ALBATROSS. ALBATROSS is one of the funded projects under low carbon next generation battery packs for electric vehicles. It started in 2021 and it will end in this July with 6-month extension. The budget is almost 10 million euro, and our consortium consists of 21 partners from 10 countries all around Europe. And our partners brought their technologies to develop battery module and packaging, battery management system, thermal management system, material and process development, dismantling, second life usage, life cycle analysis, and sustainability. So, what we aim to do with ALBATROSS. Before starting, as Marta also mentioned, BMW i3 was chosen as a benchmark battery system for ALBATROSS project. And compared to this battery system, we want to create build much more lighter, more efficient, more environment-friendly, faster charging, and much more durable battery system. To do this, we aim to reduce the battery weight, whole battery system weight by 20% and charging time by 25% from 40 minutes down to 30 minutes. And we aim to increase the peak energy density over 200 watt-hour per kilogram, and the driving range up to 480 kilogram, while extending the battery lifespan up to 300,000 kilometers. We not only want to implement innovative sensors and AI-driven BMS into battery system, we also want to develop a very fast safety detection and prevention technology. We also want to contribute to the full life cycle assessment as an improvement by between 15–20% by closing the loop with battery cathode recycling, and by using semi-automated dismantling and state-of-health, state-of-safety algorithm developments. We also want to conduct virtual analysis to integrate the battery system we develop into different kind of vehicles, such as light commercial and heavy-duty vehicles. So far, before starting to share the project results so far we have achieved, I want to mention where we are in ALBATROSS project right now. We are in the assembly building stage in ALBATROSS project. When we complete the assembly of the building, the pack, we will start to run the vehicle test and pack level test. So far, we have achieved component level results from each important work package. I will start with one of them, battery modules and packaging. ALBATROSS system consists of 16 scalable lightweight modules with embedded cooling channels for partial immersion cooling, which was developed by Cleantron, and the module achieved a 217 watt-hour per kilogram energy density, which is an almost 13% improvement over i3. And the whole system capacity is 55 kilowatt-hour, which is another significant improvement, almost 31% over i3. And the module fully laser welded, this performed by TWI, and the bus bars are laser cut by IWS. And as a result of this work package, partial immersion cooling has been evaluated for patent application. And another important work package for us, BMS, TMS, and sensing. FEV Turkey has developed master and slave architecture that gives flexibility and which can be easily adapted to the different pack configurations. And they have developed advanced functionalities like electrochemical impedance spectroscopy for cell analysis, and AI-based SOX algorithms and end-of-life determination. Also, the developed system is compatible with ultra-fast charging, and it uses partial immersion cooling by developed University of Nottingham, and printed temperature sensors and anode control charging algorithms developed by PST and CPI. Safety is another important issue for us, and ALBATROSS patented software implemented into this system for early thermal runaway detection. And as a result of this project, FEV Turkey has 4 different patent applications as a result of this work package. Let's continue with battery trays. Battery tray in this project has a structural role in order to reduce the weight of the modules, and it has a hybrid approach. The base material are produced by using extrusion and high pressure die casting by HELIOS, and the top cover and the side, the patches implemented on side walls for reinforcement, produced by compression molding by IMAN, and the base material were joined together with using different type of welding technologies. CMT was performed by CRF, friction stir welding was performed by TWI, and laser welding performed by IWS. Despite the weight reduction in BMS and TMS, we have noticed in an early stage of the project that we could not meet the weight reduction target due to the structural role of the battery tray and the cell selection. But however, we still want to explore further to understand the battery mass on the range of electric vehicles, the impact of battery mass on the range of electric vehicles, and we conducted analysis by using the GT drive. And as a result of this study, it shows that higher battery capacity, such as 72 kilowatt hour, increases the vehicle range, which is expected. However, the weight increase around 200 kilogram does not impact the overall vehicle range. But as I told you before, our project has not completed yet, and when we start the vehicle testing, we will provide the results on battery mass on the range of electric vehicles. And another important work package, dismantling second life, reuse and recycle. LATAT developed an autonomous unscrewing system for battery dismantling, and it is demonstrated in their laboratory as well. IREC has been working on the second life applications of battery pack, and they are not also working on individual cells, but they are also working on the whole pack system. And they have developed a real-time algorithm for individual cells to determine their state of repair. And they have developed a successful system which can detect the faulty cells. And they have developed a procedure for assessing the suitability of the battery packs for second life applications. And end of life and state of function estimation algorithms for maximizing the battery usage. And in parallel, Norwegian Science and Technical University has conducted compact process to recycle battery cathode active materials. And according to their results, around 80% successfully recycle rate has been achieved for lithium. And the last one is the life cycle analysis and sustainability. TVS developed a knowledge-based engineering system that automates, which helps to automate eco-friendly and optimized design and thermal management for battery cells and packs. Again, in an early stage of the project, TVS also ran 2 different kind of life cycle analysis to compare the current system with the developed system. And at that time, the capacity was chosen as 75 kilowatt hour. And as it's expected, when the capacity increases, the carbon footprint increases as well. But in this analysis, the second life application was not included because at the same time, another idea is to see the impact of second life application. And with another analysis, when the second life application is included, it is seen that ALBATROSS system will achieve a higher improvement on carbon footprint, around 31%. So regarding the mid to long-term expected impacts of the project, we can mention in 4 areas that ALBATROSS will have impact on. The first one will be immersion cooling. Due to the challenges we have faced during the development phase, we believe that ALBATROSS will have to better understand of immersion cooling for the future applications. And in terms of BMS sensors and thermal management point of view, during the development phase, we have achieved advanced knowledge in PEG sensors and thermal management, and we believe that this will improve the battery pack lifespan and facilitate dismantling for second life applications, and also recycling. And another important part is the knowledge we obtained from during the project in innovative sensors and advanced BMS. It will help to achieve a deeper understanding of PEG sensorization and thermal performance. And we believe that we will contribute to sustainability and recycling as well. We believe ALBATROSS will help to reduce the environmental impact of electronic waste and will secure the critical material supply. And at the same time, it will contribute to the optimization of battery pack design, and it will help to reduce the life cycle cost through second life use and recycling of batteries. And finally, we believe we will contribute to the automation and efficiency, which will help to incorporate robotic tools for semi-automated battery dismantling, streamlining process, and ALBATROSS will help to enhance safety. Thank you. Thank you for listening to me.
Thank you very much, Aysel, for the presentation. Also, I would like to point out that if you would like to see some more information about our presenters, there are short CVs of the presenters in this beautiful paper booklet, so you can find more information. So we are going to the last project, but not least. It's HELIOS. The project will be presented by Thomas Zentisky. He is market researcher expert and freelance consultant at International Copper Association. So the project aims to design and implement a new concept, battery packs that are intelligent, modular, and scalable, suitable for a wide range of electric vehicles, from mid-sized car to electric buses, enhancing adaptability and performance. Also, the project aims to develop and integrate cutting-edge materials, designs, technologies, and processes to improve battery performance, energy density, safety, and lifespan, while reducing cost. So, Thomas, the floor is yours.
Thank you, Marta. Good morning, guten Tag, buongiorno, buenos dias, günaydin, dobry den. I've missed somebody? No. Goedemorgen, goedemorgen, sorry. Yeah, I'm bloody German, so we expect you to understand German. Sorry about this. I'm the last speaker, so I take my freedom to tell you a little bit of a story to understand where we are and where we are going. So the 4 projects, we do each and everything except the cells. So we buy cells. We are not into chemistries. So if you prepare your questions afterwards, we're not into anode, cathode, material, solid state, blah, blah, blah. So what we did, we have to cope with what the providers give us as available cells. And we do the best what we can do with this, and we do everything. So meaning the BMS, the cloud, the safety issues, the integration into the vehicle. And we put the battery pack, an entire battery pack, into existing vehicles. BMW i3, Mercedes. In our case, it's a Bosankaya 12-meter e-bus. So I'm coming from the old world of internal combustion engines. So let's imagine you have a Golf, Volkswagen Golf, and you put a Mercedes V6 engine into a Golf, and it runs. So that's what we are doing. Just to explain you where we are. Okay, HELIOS is in the same call, awarded. So we have 18 partners, a good mix of industry, research institutes, and we have Bosankaya on the very bottom left side. This is a Turkish bus manufacturer, where we put one of the demonstrators into this. Thanks to Marta and Sinea, we had to finish in December. We are lucky that we can finish in August with an extension, because the extension, not because of COVID, of course, this is an easy excuse. We got the extension because it took us more than 1 year to sign a contract with a cell manufacturer. So we had to select, and some cell manufacturers did not want to work with us, others provided some very strange data sheets, and we did a very big, messy Six Sigma analysis, how to combine cells. Because, so the objectives are clear, so weight reduction, volume reduction, faster charging time, extended lifetime, better carbon footprint, better view on sensorization and thermal management. Explain what is HELIOS, a little bit different than the other 3 projects. So in HELIOS, what we do is we mix chemistries. So we have NMC cells and we have LTO cells. So we have high power and we have high energy. And we put one box, or we have one box, same size, with high energy modules, which are pouch cells for us in our case. And we have one box, same size, with high power cells, prismatic cells, Toshiba. So 2 different chemistries, 2 different cell types, but the box is like the same. The idea why we do this is to have a range possible, like a toolbox, or let's say a shelf in a supermarket. So you want to have more cheese, you want to have more tomato sauce, you want whatever. So you pick, you can combine high energy, high power in a mix. Give me more range, give me more power, give me faster charging. And in the middle is a BMS, which is wireless. So that's, in a nutshell, the idea of HELIOS. But of course, please go to the website to better understand. So the different thing is here. So we have a mixed chemistry, a modular approach where we can combine and arrange, adapt power or energy density. And coming to numbers, you can read this afterwards, we're failing. Why we are failing? Because of the compromise. So we want to put one demonstrator in a small Mitsubishi car and one demonstrator in a 12-meter e-bus. So all the objectives, power density and energy density, we cannot do it with our demonstrator. So we have to decide and we make a compromise. So we're failing a little bit on the energy density, as you see on the right side. So we're not meeting the 240 kilowatt hours per kilogram, and not the 500 watt hours per liter. On the very right, I put the 232 whatever. This is on module level. Cheating. On pack level, we're not that. But on the other side, you see on the power density, we are way over what was expected. So our pack in the demonstrator is really power. We can do energy density with a different configuration and different cell chemistries, of course. So the concept itself, it works, but not in our demonstrator. We cannot do everything in one demonstrator. We have to decide whether we do this or that one, and we went rather for the power density because of the fast charging as well. And we promised in 6 minutes 80%. We are at 65%, which is not too bad. Probably when we have 10 minutes, we are over 80%. I hope that we can prove all these in August then, when we finalized the project. And you are invited to join us when or wherever is the final project event. So what we can claim is here. So first of all, we have finalized, of course, the mechanical design. So lightweight is proven. LCA is also proven. So we use Bayblend from Covestro, a plastic material which a high recycled content. We use copper, aluminum in bus bars. We have an approach which is easy for dismantling and recycling. We have an energy management introduced algorithm into the battery management system with advanced algorithms for state of charge, state of health, state of X, whatever, which really proves the longevity of the system, of the battery pack. Oh, that's strange. I don't know what happened here. Below there were some figures from the high power and high energy aging models, basically saying, okay, we can do up to 2,000 cycles, 3,000 cycles, whatever, in a given temperature range, in a given charging range. And there is basically, because we do the super fast charging only from the high power side, to avoid that the high energy cells, which are more effective to the aging, would degrade. So we can really say our battery can easily live for 10 years and 300,000 kilometers. The battery management system is wireless. So meaning we don't have a harness between the modules and the battery management controller, which is easier for dismantling, which is cost effective. Of course, you have a communication question, maybe. This is solved, and it's proven, so it works. We have implemented the SOX algorithms. We have also developed in the project, thanks to Vitesco, which is now part of Schaeffler Group, a so-called multi-sensor unit. So one box which measures pressure, acceleration, humidity, different gases to allow detection of hazardous situations. So it's in sleep modus normally, but then it wakes up and gives an alert to the cloud and to the driver. On the power electronics side, we have developed a system relatively complex, of course, so meaning we add costs, of course, yeah. If you are from an OEM here, you would say, what about costs? Yeah, of course, we have costs because it's a multi-level DC-DC converter with a neutral point clamped. But on the other hand, we save costs on the chemistries because we can use relatively simple cell chemistries on the high power side and the high energy side. So here's a trade-off, obviously. On the LCA side, as I said, so we're mixing chemistries, which is complicated. You have NMC and LTO. On the recycling side, there's not much information about how to recycle then a pack with two different chemistries, anodes. We did some research here. There's a paper also published, put the DOI here. But you see the initial figures are 88% lithium and more than 90% of the other materials, so quite promising. Further research has been done. We do this on sub-pack level and on module level. Also regarding the impact categories, so what is the water use, the ozone depletion, etc., and what is the impact of the different components into the battery pack. So now, as Marta said, I'm very glad and very proud to be part of the Collabat cluster. Collabat means we all 4 projects start with the same objectives, and normally projects are competing. So you are doing this, we are doing that. We are trying to overcome this and say, hey, let's work together. So we have the same challenges, we have the same objectives, we have different approaches. Of course, we have to respect confidentiality issues, IPR, etc. And but what we did, so the different story here is of course, we did dissemination, webinars, events. We went to Battery Innovation Days in Barcelona last year, TRA, etc. What we did is we had closed-door discussions in at least 3 sub-clusters. We call it sub-clusters: sustainability, A, testing validation, B, and BMS, C. And this means the different experts from all 4 projects sit together virtually and discuss challenges, etc. And then afterwards, if we think, oh, that's interesting for the grand public, so we went to a webinar and say, okay, we can present some of the results. But first of all, it was for us to understand what are the challenges, what are the different approaches, how can we learn from each other. So really use the synergies and not the competition of the projects. And that's something I would encourage other projects as well to do so. Digital twin, of course, we use artificial intelligence for the algorithm, machine learning, also to optimize the performance. And we have a fleet management platform, which then allows fleet manager to calculate the CO2 footprint and also to organize the logistics of charging. So it's quite a complex, so it's 2 things. So first of all, of course, there's a closed loop back to the BMS system about the battery, a single battery in the car, but there's also big data analysis, collecting data from all the cars, at least in one fleet, and make some analysis, okay, are they effective, are there any issues, etc. This is split between different partners, the IoT platform, the fleet management platform, and the digital twin for self-configuration, and the state estimator of SOX, meaning enable then the battery to live longer and stay longer. And ultimately, of course, this data would be then feed into a battery passport, which was not part of our project because we were too early. Before the battery passport was a big hotspot topic, but of course we can cope with this. So I would like to be here in 2030, not sure. But if you ask me in 5 years, so HELIOS, what did you do? Well, okay. We have a different concept. We have a hybrid modular system, which is a different option. Normally OEMs go for one single chemistry, so one battery for each model. We have a toolbox. I hope this works for some OEMs. Of course, we can reduce the charging time and the weight and the lifetime of, we can increase the lifetime of the battery. So meaning that ultimately, hopefully, we help the end customer to be more comfortable using an EV. And me as a German, we always say range, range, range. Otherwise, I don't drive 300 kilometers every day. But if I have the option, it would be nice. And if I have the option to charge in 6 minutes 80% of my car, it would be nice. So given this feeling of security, reliability, I think this will raise the acceptance, hopefully. The wireless BMS will be tested outside of HELIOS by other OEMs already, so this is also a nice key exploitable results. The multi-sensor unit as well. And then we show with our lightweight and disassembly and eco-design friendly concept that we are going towards more sustainability, second life usage, easier recyclability of batteries. The IoT digital twin platform will also enable fleet managers, ultimately maybe single customers to make a better use of the battery. Society, yeah. So we need experts. So meaning, on one hand, we have a challenge with the artificial intelligence, the algorithms. On the other hand, we create demand. So university, research institutes, they have to cope with this, and they are asked to give us the people. Because the digital twin ultimately will also reduce the cost. Total cost of ownership. With the second life market, we will also give opportunity to other business models, to a longer use case or different use cases of batteries. And then what is our contribution? Of course, we have issued several papers, articles, also academia material for teaching courses, and there are 2 patents under consideration for the moment. And that's it from my side. Thank you.
Thank you very much, Thomas, for the very interesting presentation. With this, we have concluded all the presentations for the 4 projects. So I will pass the floor to my co-moderator, Bozong Kambaya from BEPA, the Batteries Partnership, European Batteries Partnership Association. Again, thank you very much for stepping in the last minute. So the floor is yours for the Q&A session. Thank you.
Thank you, Marta. Thank you all. I'm Bozong Kambaya from BEPA. Just send my colleagues, Dr. Franz Geyer, also a member of the executive board of BEPA, his apologies, and also he sends his regards due to the unseen circumstances. He couldn't make it, so I'm stepping in for him. Thanks all. Thanks for the great presentations. These projects, this portfolio of the projects for us coming from the more of a battery sector has a very special place. We usually have to pinch ourselves and say, okay, we don't make batteries to make batteries. We don't make batteries to have higher energy density per se. We make batteries to have a better cars or transport. Also, on the other extreme, we usually think, I mean, a little bit going against Thomas's notion. I hope it doesn't give that impression, but the automotive sector thinks of this box that produces energy, and it's just something that you can look at it as a black box. There are a lot of things going on there, but these projects really make that meeting point. So you're touching on a very kind of full of undiscovered areas, and thank you for that. You have a special place, as I mentioned, in our heart of the partnership. So with that, I just want to open the floor to our audience. If there are any questions from the, yeah, please.
Hi, thank you a lot for your presentation. I'm Lisa Lou from CEA. I was wondering, I saw that you studied, so you did design for recycling, design for disassembly. Have you studied and have you checked at design for maintenance? And have you studied if it's interesting or not to maintain a battery during its use life? For example, change cells, and would it extend the lifetime, or did you study this? Thank you.
It works? Yes. Okay. Thanks for your question. And yes, so the eco-design action we implemented in what concerns the facilitating this dismantling or easy disassembly, it also considers a KPI. The project also have a KPI concerning the maintenance cost and the possibilities to replace modules, even cells, but I guess would be more cost-effective, etc., to work at module level. So we have this KPI, but well, since our battery have been assembled recently, it's in the test bench, etc., we are still putting numbers together and calculating this. So the real effect on the cost of maintenance, I cannot deliver it to you, but I am committed to do it by the end of the project. So in end of March, this should be delivered. But yes, both objectives are on the table. Repurpose for second life, but also facilitating the maintenance as a measure to extend the life of the battery also.
Thank you. Any other questions?
Thank you. Jeremy Warren from AP Plus Laboratories. I noticed that in a large number of cases, there is a desire or an implementation in cloud-based computing. Now, granted, I understand fully that when these projects started, a lot of the capacity for edge-based computing was not as advanced as it is now. However, given the various vulnerabilities that have been found, for example, in 3G, which is why it's being moved out of place, so if you move to 4G, 5G, what if there are vulnerabilities that are discovered there? And so is there the opportunity, is there an idea potentially to also potentially consider edge-based computing systems? Or are the models too complex? Are the computational costs too high at this point?
Anyone would like to take the question?
Thanks for your question, Warren. I'm definitely not an expert, not on cloud computing, not on edge computing. Definitely our system has an edge device in there, and it is a possibility that we upgrade to something like this. The real question is always, what do you want to control with these parts? The cloud gives the option to do it like an over-the-air update, to do these kind of things. The edge device, this is possibly not that straightforward. The cloud gives the challenges or the opportunities to really do some kind of fleet management, overall assessment in this context.
Please, yeah.
No. Hello? Yes. Well, the question is, or the question, thanks for the question, and the question back is, why do we need real-time and 100 milliseconds responses, etc., in a battery pack? So we need data storage, and data storage is in the cloud. So we don't need the high sophisticated, which is also CO2 impact. So artificial intelligence, we should bear in mind that the increase of CO2 will come from data centers because of real-time operations. So if you process every 100 milliseconds, every data coming from a battery, for me personally, it's completely nonsense. You need to store the data and analyze data in data packs, big data machines, etc. But you can do this once in a day, once in a week, once in a month. So there's no need for really this high sophisticated artificial intelligence, real-time operation coming back and forwards, in my opinion.
Okay, that's a good point. So basically, it's overdoing if we go for the real-time state of health, state of life measurements, okay? Even a state of charge, you think? So, I mean, that's, at the end of the day, okay. Once per day, okay. That's the routine. Thank you. Please, yeah, thank you.
Hello, Tutku Özlem from Asaş Alüminyum, Turkey. We are a partner of MARBEL project, and in this project I know the challenges that we have faced within the project duration. I wonder what kind of challenges have you faced in other projects, and if they are same with ours. I just want to know the other projects' opinion about it. Thank you.
Thank you.
Maybe I can start with this. I have been involved in this project in a late stage of the project. I've been coordinating this project for 5 or 6 months. But the main challenge we have faced during this, I have faced during this process is the production phase. There were quite a lot of delays that we couldn't foresee before, and there were a lot of material supply delay as well. For this reason, right now we are also facing with another delay with the production as well. I can only tell you this.
Yep. Is it working now? Yes. For Liberty Project, there is a multitude of challenges. Some are technical, some are organizational. Maybe one thing I would like to highlight, especially as Aysel also mentioned it a little bit, you need consistency in your team. You need a very dedicated team for, in our case, a 4-year project with a phase before, and every change usually involves more challenges. So we were very lucky to have a very consistent team throughout the project, so we could tackle the technical challenges that in many cases can be solved, but they need dedication and lots of dedication. It's mixing, in our case, 14 partners with different backgrounds, different cultural backgrounds. You need to come a common conclusion, and in our case, we had to build a battery pack that lasted all our testing activities. And doing that continuously for such a long time, I think that is the main challenge, actually.
Well, nice to see you as colleagues. Well, you already know the challenge, but I wanted to add to what Thomas said concerning the availability of cells. No? That was one of the big challenges, and also why these projects have been delayed, as Thomas said, in our case the same. The problem of availability of cells. We started with one type of cells. When we moved to prototype stage, we needed to change the cell and then redesign. Okay, that was the main challenge. The other ones, I agree, coordinating everything. We have all the value chain of the battery there, building at a prototype TRL7 level. So you need several components from different partners that arrive, maybe, well, checking and coordinating all this and the timeline, etc. It's very challenging. And in what concerns the housing, I think there were a big challenge on these high-performance extruded profiles with a high percentage of scrap, recycled scrap, and the joining of these profiles, having the screws, the cooling system integrated in the frame, etc. This was also a big challenge, but well resolved by the help of ASAS, Sintef, and EURECAD. So,
thank you. Any other questions? Yeah, please.
João Miranda from Cinea. I'm a colleague of Marta. So first of all, thank you very much for your presentations. It's very nice to see that when topics are clear, have clear targets, you find different solutions to reach them. So I think it's very interesting, and it really shows the different options and allows us to explore different options. So thank you very much. Over the sessions, over these last days, we keep seeing very impressive results. 99% efficiency for power electronics, 97% for motors, double the lifetime. My question is for all of you, regarding the lifetime, how sensitive is it to actual working conditions? So will the increase in lifetime be maintained for a wide range of working conditions? Or, for example, if the user is driving a bit more aggressively, if it's in Finland or if it's in southern Spain, how is this taken into account?
Yeah, thank you. Very good question. I mean, it also links to the misperceptions about the batteries and the working conditions and the lifetime. So,
unfortunately, on my slide, it was like Chinese or whatever. So we did a very sophisticated study on aging. And of course, the temperature is the main. There are two parameters, the temperature and the charging rate. In our case, if we consider normal Central European temperatures, meaning not going beyond 40 degrees centigrade with cooling, and not going beyond 10 C charging rates, which is already very high, then our system proves reliability of 2,000, 3,000, 4,000 cycles without much degradation. And the sophisticated cloud-based algorithms with monitor state of charge, state of health, etc., and loop back into a system which alerts the driver, hey, maybe your driving style is not appropriate, or whatever the OEMs wants to put in the car, he can do this, yeah. So, yeah, we can say even in real life conditions, we think in Central Europe. Of course, extreme conditions, extreme temperature conditions, extreme charging rates would degrade the system. But in a normal way, even with a driver style behavior, we can cope with this.
thank you. Anybody else? Yeah.
I could add to that. We are using totally different cell chemistries here, but due to our relatively sophisticated and complex cooling system, we are definitely able to keep the battery in a very good operating conditions. So driving style is not so much of an issue. What is an issue is charging. So we were able with this cooling system to fast charge our cells. But if you do that too much, those cells will not last. Those cells. This is changing, technology is evolving very much, but those cells we have would not last forever. So there is a huge implication on that topic. But you can do it, we were able to show it, but at a cost. It's a very high compromise on that.
Okay, thank you. Any other questions? Maybe one from my side. I mean, Werner, going to the domain of lifetime and aging and safety and other kind of rather externalities. You used a sentence that might be a little bit controversial. You said that the trade-off between safety, performance, and durability, and it's just a little bit blasphemy, trading off on the safety. So just if you could give us, because we also had this conversation yesterday for the next generation of the batteries and the technologies and development of the technologies like solid state batteries, needs a little bit of a rethinking about how high we keep these KPIs, and are these KPIs necessary to keep them all at the same time? So maybe you have a better vision of how things work in practice.
Thanks a lot, Bozer, for this definitely controversial question, but my background is actually vehicle safety. That's my original background, and you cannot have ultimate safety. So this is always a compromise. You have to address what is likely to happen and what you can do against that. You cannot protect a vehicle against a train crash. for example, to put it very, very drastic. But you can do, and that's what vehicle safety is all about, you can deal with likelihoods, and vehicle safety increased a lot over the last 40 years since seatbelts were introduced, the airbags were introduced. I put this analogy for some very good reason. A battery is a little bit like an occupant. They want around 20 degrees Celsius, maybe a little bit higher, let's say 23. They do not like high accelerations, and they do not like deformations. All this combined gives us a compromise. We have to, we cannot put a tank around, we cannot put a battery in a tank. Then we are very bad on circularity, mileage, and these kinds of things. So it's always a compromise, and safety is as well. I showed a little bit about our mechanical testing and crash testing. Currently, we are probably, and this is also controversial, a little bit over protecting our batteries. They are not catching fires continuously in crashes. That's good, but we could potentially, and our batteries, depending on which chemistry, which format, which way and how do you protect them, they endure quite a lot. You can load cells quite a lot mechanically as well. And the same is for other reasons. So it is a compromise, and I'm happy to discuss more on that later, but we have to understand the characteristics of the cells in order to optimally integrate them.
Exactly. So maybe a follow-up question could be, in your opinion, how we can go a little back into the development process instead of expending a lot of money on at the system level and the expensive tests that you do, that we talked a little bit about. So if we go a little back into the chain and get to this, make sure that we make the cells that are safe enough to, again, give us a little bit of a relaxed constraint at the system level that you're working.
Cell chemistry is definitely one point, but as these projects were not dealing about the cell chemistry themselves, I would like to focus on, let's take a given cell and integrate that in an optimal way. I showed some metal can cells that you can put at least in 2 directions in a vehicle. And there is one that is likely to be loaded higher, and the other one is likely to be loaded higher in a typical crash scenario, just to put that here. You can, of course, focus also on other areas, like a very good cooling and a good BMS. Use cells that are reliable. That's a very important thing. But do your design decisions early on and not compromising too much on modularity if you give up safety for that. That would be my point.
Yeah, thank you. Any other comments on that? On some sort of a better understanding of the compromises and the trade-offs that we can make. And again, the battery community is not well aware of the possibility of those sets of compromises that could be made. Any other questions? Yes, Michael.
Thank you, Michal Klimasina, a bit insider. So a question. And we have discussed that, I think, last week. The KPIs for these kind of projects are at the battery pack level, in terms of energy density and in terms of cycles, but it is very much dependent on the kind of cells that you actually use. And as you have mentioned in your projects, you have did some assumptions at the beginning, and then you've changed maybe the cell chemistries in the meantime, which affected the final KPIs, so in terms of total energy densities and cycles. So my question is, do we have correct KPIs? Should we use the absolute one, or should we maybe introduce how the other work on battery packs influences the initial cell performance? In example, when we have a cell with specific energy density, if you calculate it per battery pack, it probably decreases. So maybe that contribution is minus 10% or minus 5%. In the same way, if the battery cell is capable of last 3,000 cycles or 2,000 cycles being integrated, what would be the performance? It's certainly probably maybe it could be improved, but what is the influence of your work? So could you please elaborate a little bit on this in a way that we can as well better assess the contribution of your projects and to separate it from the initial input from cells? Thank you.
Yeah. Very good question. Anyone?
Michael, that's a good question, a very important question. I want to say one thing to that. The battery system depends on the cell. That's the main part that we have to deal with. And cell chemistry, cell types are evolving very, very quickly in the last couple of years. We are very fortunate for that. But 10 years ago, nobody would have believed that we reached those rates that we have nowadays. They're still promising much more than that. And actually, every month you read something that the next breakthrough is around the corner. Not that quickly. But we always have to consider the system, the integrated system, and that is cell dependent. So yes, you're probably right. That putting the KPIs like they were in these calls are a bit tricky. Still, for the system we used, we are not cheating here. It's working, it's integrated, but it's different. We cannot directly compare those results here. So yeah, that's what I can say to that.
Okay, in our case, that we, as an experience of changing cell in the middle, on the course of the project, I agree with here. It's very dependent. The configuration of the battery, how many components you have, etc. In our case, for instance, we increased the number of modules, so the components, etc. That compromises in a certain point the weight reduction. I don't know, the way I'm thinking now on life, it's like maybe setting boundaries of the kind of cell that we want to work or the kind of vehicle, because we started working or targeting a high performance vehicle, sportive vehicle. But well, maybe defining boundaries and base it on this frame, set KPIs for weight reduction. Otherwise, it's what it was commented. The system and the pack is very dependent on the cell, and depending on the kind of cell you put there, you will have more cells, more components, less cells, less components, so more weight, less weight. Yeah, in our case, I say we have this experience, and we could even calculate that at the end of the project, maybe at design level, of course, because we don't have the prototype with initial cells.
Great, thank you. Anybody else? Yes, please.
Thanks, Michael, for the good question. And my naive answer back to SIDEA and the Commission is yes. You need to challenge us with very sophisticated KPIs, but now, don't expect that we can promise and then we can prove we can promise everything, but we cannot promise prove everything at the end. So in our case, we promised everything. We were naive. We were thinking we get the cells to prove high energy and high power at the same time. In our case, HELIOS, we cannot do this in the demonstrators. We can prove this on paper, in the concept, with the next generation. And as Werner said, the cell chemistries are evolving so fast and so quickly. So probably in 2 years, we have the better chemistries, and we can redo this exercise again. But for the demonstrators, so the real type world, we are failing in some, and we're showing on the other side over. So in our case, so our power density is much higher than what we promised, but our energy density is not. So that's where you need to live with. They're saying at the end of the day, the proof of concept is there, but maybe not all the KPIs, the boxes are ticked.
Thank you.
Hi, Alfonso from the Barcelona Supercomputing Center. My question is regarding, all your solutions are slightly different approaches, the same objectives, more or less. My question is, regarding your TRL, is up to 7, how far are you from the mass scale manufacturing, production, assembly? Yes, thinking about TRL up to 9 or let's say industrial uptake.
Very great question. This is the talk of the town now. How we get to the next level in terms of scalability and competitiveness. So
Maybe I can give an answer to you. For the mass production, I can easily tell you that our system is not suitable for mass production, especially considering the module production, because most of the delays were happened during the module production phase, and it is quite labor-intensive process. For this reason, I cannot tell you that this is suitable for mass production.
thank you. I mean, in some way, it also addresses previous questions. The fact that if we go with the chemistries and think of, okay, it's going to increase the energy density by 10%, and we go with the sensing components that is already there, it's a moving target of, okay, this is the auxiliary component will really add so much that it will compromise the cells or the chemistry's development. So if you want to get out of that kind of a thinking, it's just, okay, let's also decrease the size and weight and scalability and the manufacturability, increase the manufacturability and scalability of the components, of the auxiliary components, of the BMS, of the etc. So a little bit idealistic view, but what's your take in general? So we can go component by component, or in general you think, is there a taking off the shelf thinking there? Is there battery sector should also think about these components as some sort of its own kind of a children, going with that through the scaling up in the gigafactories? So that's also something that we are struggling a little bit to see how interconnected sensing sector is with the battery sector moving forward, and tailored design, tailored solution. What do you think of that? Is it some sort of a good escaping point for this challenge?
Combining the two questions here. As Aishal well said, so it was not the objective to have a TRL 9 level battery pack. So we are prototypes, so we are demonstrators, and that's not something you can move easily from now to next year to a serious production as a battery pack level. In our case, yes, we have a wireless BMS system which will be used by 2 OEMs this year, next year. We have a multi-sensor unit which has a patent and will be used by OEMs. So there are different components out of the projects, lightweight structure, disassembly approaches, which probably can take into another development of battery packs with a different layout. So here's the impact of our research. So we show the direction. Okay, this can be done, that can be done. Thermal management, like Valeo did in Liberty, with the very nice combination of spray and immersed cooling, it will be done at OEM level. So we give the inputs and they will be realized, but not in our entire project cases. So not that the battery pack with all the components will be done in a serious production in a car, but we give the inputs here and there so that tier ones and OEMs can decide, okay, this is a nice approach, so we will use this in different configuration.
Mm-hmm. Yeah, I totally agree with Thomas. Our batteries are not a battery intended to scale up to be the battery of certain segment of vehicle or certain. I think they are a platform of demonstration at a real scale, integrated in real platform vehicles of different number of innovations, from materials to digital solutions, etc. Well, different technologies that are demonstrated at that level and serves as a platform of demonstration to take these results and implement it in the battery of one OEM or in the one another product. But I don't see the battery itself of MARBEL of something that will be scaled up and sold in a mass production. I see the components separately and the technologies separately. Yes, that's it. And the manufacturing readiness level of the components, of the sum of the components, it's already ready to be manufactured and integrated in future batteries.
Yeah, and the completely same here. We built the battery as a demonstrator, integrated in an existing vehicle, built on existing requirements for this battery pack then. So this will for sure not be upscaled, because the vehicle is not even manufactured anymore. There's the next generation already out there and the next generation requirements there. But all the methods and most of the components as they were designed can easily be transferred to the next generation. They need a little bit of work in some cases. They need a little bit on work probably also on legislation in other cases. We're talking here about the main switch. I think as far as I know it's still required to have a physical main switch. The semiconductor one would be a good alternative, and I think it was shown that it is as reliable as a physical one, but for legislation reasons that's not the case. Many of our safety concepts are patented, are already applied somewhere, or are in the process of being applied. So as the colleagues before said, it's the components, it's the sub-ideas that are used. It's not the complete process that will be transferred, and exactly this is the way to go.
Okay, please.
Me again, sorry, this is not a review meeting with all the senior questions. But so maybe for all of you, you mentioned, I think it was Werner, the battery pack is made for the cell. Cells are always changing. For each of the projects, what is the technology that you developed that is ready to be moved for the next cell generation?
That's basically continuing what we just said. The way how we integrate this cell-to-pack approach can be directly applied to the next metal can cells, whatever size they are, but they need to be metal can cells in order to be used the same case. So we got a very densely packed pack, and the cooling system as it was would work. Probably a little bit over sophisticated for today's cell chemistries if you want to reach the same charging rates. If you want to go higher, then probably it would make sense again. The BMS is basically freely available Fraunhofer BMS that is used, is continuously evolving, so all the knowledge that went into this is available at Fraunhofer. You can have it now. Most hopefully now. The cloud system that is developed, was prototyped, is working, can be applied, and is further worked on already. So we are already there on the next part. The pressure sensors, all these kind of things are being in the process of being either used or adapted again to be used. So I think that was most of the components we were talking about.
Yeah, it's fine to me to train for review meeting because I will have it in next month, so don't worry. and yes, I think despite it's true that we posed a lot of responsibility in the cell, no, that influence a lot the battery. I think main part of the results we get can be considered independent on the cell. I'm thinking on the housing, lightweighting the housing, using recycled materials, integrating cooling systems in the housing, the non-welded fasteners, the digital part, this software as a service, digital cloud computing algorithms for prediction of the state, the BMS to have it modular and scalable and as a tool to facilitate repurpose, etc. All these results, I think, could be implemented in different kind of cells. The more tricky part of the cell, it refers more in what concerns weight, that's true, depending on the number of cells, etc., and performance, lifespan, and charging, that you need to know exactly how the behavior of the cell, temperatures, degradation, all this, to design a proper cooling system. But yeah, I think that there are many advances we made that, in fact, we were playing this game of working on cells independently, and we have this redesign, so we keep it the geometry, no? So all the things we were working on cells that are given, so developing technologies that are a bit independent on what cell you get, except the thermal part. Yeah.
Okay, I think we have time for one last question, if there are any. Okay, so thank you all. I think we just touched upon some areas that for us was also new. So I had the impression that we are still a little bit distant from some sort of a comprehensive standardization at the pack level for now. That adaptation to the different chemistries, to the different technologies, as you mentioned, there's a step should be done, and then the companies to be really easy for them to go change the technologies and the chemistries and the cells. There is a huge step of adaptation at the pack level that should be taken care of, among others. So thank you very much, very enlightening for us. Thanks also to the audience for taking the time and making it here despite the disruptions in the public transport, and very grateful to you. And thanks to Marta, everyone. Please enjoy the coffee break and have a nice rest of the event. Thank you again.